later.
Yes. Okay, cool.
Okay, sure. Thanks. Mm. Okay, can you guys see my screen? Is it showing me offline? Okay, can you guys hear me? I'm having some internet trouble.
Yes.
Yes.
Okay, sure. That's fine. So today I'll be starting with the basics of PowerPoint. So in case anybody, like if people know the theory, I have three problems which I'll try and do at the end of this class. So like, you can, whoever knows the theory can take a screenshot and maybe try doing this while I build up the theory. So if you want, you can take a screenshot of these three problems. I'll give a moment. Okay, I hope you have taken the screenshot. So I'll start now. So our topic is no great power comes without a great point. So you all know about cyclic quads, right? And the good thing about cyclic quads is that they give us very nice angles. So suppose I have a cyclic quad ABCD over here, and they intersect at a point P. So can you show that AP times PC is equal to BP times PD? That's one of the elementary riddles. Try showing this. And okay, thanks. And if possible, try to speak up. I'll try checking the chat, but I'm not sure. I'm not too good at checking the chat while teaching. So yeah, also I'll probably be a bit fast on the theory. So do feel free to ask me to slow down if you guys have problem understanding. So yeah. So anyone on how we can show this?
Um, that angle ACB is just angle BDA due to
Um,
cyclic property and angle.
okay, which one? I guess this one and this one, and maybe this one and this one. Okay, I think
So
you
we
are
can
correct.
show.
Yeah. Yes. Go on. Okay, never mind. I'll continue. So, okay, can you guys see why angle ACD is equal to angle ABD and angle BDC is equal to angle BAC, right? So these holds because of the cyclic conditions. So from there, I have triangle APB is similar to triangle DPC. And so from here, I can get AP by DP is basically PB by PC. So writing it down and cross multiplying, I'll get this result. Right. So what is interesting about this is that for a particular point P, whatever chord I choose. So for example, I'm choosing another like chord through P. Say this is EF. So now PE times PF will also be equal to PA times PC because AECF is also a cyclic quad, right? So I'll also get this is equal to PE times PF, right? So I should intrinsically give this a property of P because it's invariant of whatever chord we choose. So we can also take this chord and and at that time we can get this times this is equal to AP times PC, right? So now what our goal is, if we can find a good representation of what this value might be. So we can, since this does not depend on the chord, we can choose a chord like we have the freedom to choose what chord we use. So can anyone suggest what is a nice chord that we should use to approach a nice representation of this value? Guys, something. Yeah, similarity. Right? Okay, can anyone suggest me a very nice chord which we can use? Yeah, we'll come to that, but how do you get it? Good, diameter, yes. So let's take, let me rub this first. Yep, where's it? So we can take the chord, suppose this is the center of the circle. So I'm taking this, and let's say this meets at y and this meets at x. So now, what we want is px times py. Now look, what is px? Px is ox minus po, right? Okay. This is clear. And what is py? Py is oy plus po. Now the good thing about this is that ox and oy both are the radius of the circle. So let me call this radius r. So I have r minus op and r plus op. So this reduces to r squared minus op squared. So this is a pretty nice thing. So what this basically tells us is that if we have a circle and a point P inside it and a point O, which is the center of the circle, then whatever chord we choose through P and say it intersects at A and B, then the value of PA times PB will always be R square minus OP square. It is invariant of whatever chord we choose. So this gives us a lot of power over like what P can do because of this invariant thing, right? And okay, nice emoji. Thanks. I'll also keep checking this. So for P inside, we get this expression. Now let's try doing something similar for P outside, right? So why should that be left out? Uh, I'll go over this a bit fast. So this is A, B, C, D, let's say. We have a cyclic chord and they meet outside AB and CD at P. Then PA times PB should be equal to PC times PD. Can you guys see why this is true? Can you give me a yes or a no?
Yes, because angle
Yes.
PCB.
Yeah, this is also angle change.
Yeah.
In this angle, this similarity.
Right,
Yes.
right. So I hope you guys can finish this. So we also now need a good representation of what this can be because this basically tells us that whatever chord we choose passing through P, so that times that value will always be like independent of the particular chord we choose. So here also I'll go a bit fast. So this is the O, and then if you join OP, say this is Y, this is X, then the value of PX times PY will be PX is PO minus OX and PY is PO plus OY, right? And here also OX and OY are the radius. So I can just write this is PO square minus R square. Um, So something also similar to this is like this, we have r square minus op square. And when the point P is outside, the sign has sort of switched, but the terms remain the same. We have op square and we have r square. And let's just do this case when P is on the circle. So in that case, we see that the quantity OP square minus R square is equal to R square minus OP square is equal to 0. So this is the third case. Just wait for it. So what this motivates us is to define a quantity. And what that quantity is, it's called power of point. Let's say P with respect to whatever circle I'm choosing. So let's say the circle is omega. So what this basically means is that power with respect to omega of the point P is defined to be OP square minus the radius of the circle. And why this is useful is because if this is greater than 0, which means I'm in this case, so this will imply point P is outside the circle. If this is equal to 0, which means OP square equal to R square, or other words, OP equal to R, this means P will be on the circle, so belongs. Also, by the way, someone is, I guess, unmuted. Can you just mute yourself?
9833
Han.
491751.
Wait, I can. Cool. And if this is less than 0, then I can say that the value is r square minus OP square, which is positive. In that case, P will be inside the circle. So based on what this value is, I can sort of determine where P lies with respect to the circle. So is this part clear? I think I was a bit fast.
Yes, clear.
Yes.
Okay, cool. So yeah. And now let's see what is the converse of power of point. So this was power of point, and let's look at its converse. So what this basically says is that if you have P and you have two rays like this, A, B, and let's say here is C, here is T dash. Never mind, let's call it T. And it satisfies that PA times PB is equal to PC times PD. Here we have a condition that P should either lie on both the segments AB and CD, like this, or it should lie outside both of these segments. So it cannot happen that P lies on one of the segments and outside the other segment. So this we are not taking into consideration cases like this, right? So this will not hold, only this and this will hold. So now that's clear. What this claims is that this implies ABCD is cyclic, or ABDC as I've written. Can you show this? A quick proof would be helpful. Let me check the chat. Anyone on why this is cyclic? Okay, guys, come on. Why is this true? I'm not moving on
Like it's
unless you
just
tell.
similarity, right?
Yes, it is similarity. So
Like
what? Yeah,
PA
go on.
PA by PD equals PC by PB, and we have
Yeah,
an
so,
angle in
which
common, so
implies that
yes,
right.
yes.
So
yes,
you
yeah.
get two equal angles. There is also another cool way of doing this. This
Similarity
is
like
right. Similarity is the right idea. Good, guys. So, but I want to tell you another proof, which is basically a bit slick, which is already know that if this is cyclic, then this is true. So you somehow want to use it, right? So this notion is very common in geometry, like phantom points. So suppose you assume this is not true. So and you draw this circle through ABC, and let's say it intersects again at D dash, right? So from the theorem of power of point, you know that PA times PB is equal to PC times PD dash. This should be true because we have proven this in the last case. And now what this is telling us is that PA times PB is equal to PC times PD dash, PD, right? So now if you take these two, it says that PD dash is equal to PD. But this will be impossible if D and D dash are the different points. So D and D dash must be the same points. So in reality, D is just this point, and we get that ABCD is cyclic. So
Are the lengths
mean,
directed here?
no, we are not taking directed lengths yet.
Okay.
This is just the magnitude. Okay, so is this proof understood? The basic idea was phantom points, which is maybe a new idea to a lot of you.
But like it's not. It's just assuming that that's
so
easy.
what
Yeah,
do phantom
it's
points really do?
so it is
Like what is the
basically
definition?
it's not a definite definition sort of, it's basically a problem solving technique where you assume a contradiction and you sort of phrase the solution in such a way that if this does not happen, then I might get a contradiction somewhere. So for example, you're taking a phantom point which really does not exist because this point is really this, and now you are using this point to do geometry on it, and then you are getting that this point is actually this through this. So this is your
Okay, okay.
conclusion. So you have used a ghost point which is not existing, to show this is true, right? And then you can show that the ghost point is actually what you wanted. So phantom point is very useful when you want to say prove three lines conquered. So you can say that this is a point, and then the other points you can just assume, and then show that this is like these three are collinear at the last. So this is basically a sort of how you frame the solution. Okay, I hope that was clear. Next, what are we supposed to do? Oh yeah. So okay, this was a quite a bit of power for a point. Now we want to develop more on this. So we had one circle and we were quite happy with it. So let's take two circles. So now we have two circles, omega 1 and omega 2. And now we have this question that what is the locus of all points P such that the power with respect to the first circle will be equal to the power with respect to the second circle. So
You're talking about radical axis.
Like the radical axis
precisely,
is.
yes.
Yeah.
Okay, I think a lot of you know, so I'll skim through this a bit. So when we want to find locus, a good approach is to draw a lot of diagrams and see what's coming and what's not coming. So let's see, you have this. Can you identify 2 points which have the same power with respect to both the circles?
The two touching points.
Intersecting
They
points,
both
yeah.
have power 0, right?
They are
Yes.
intersections.
Right. So this point and this point both have power 0. So both of these must lie on whatever locus this is. Right. So now what I'm gonna do is I'm gonna prove that this is actually a line. So our claim is this locus is actually a line perpendicular to, okay, let's say the centers are O1 and O2. So it will be perpendicular to the line joining O1 and O2. Can you guys try this for a bit? A warning, you might need coordinates. So yeah. You can just tell me your ideas, that will work as well.
Do you really need coordinates or like can it
I mean,
be
if you can provide me a synthetic solution, it would really be nice. I forgot what was the synthetic solution. But
I
using
really have
coordinates is
never seen a
easy.
synthetic solution for this.
Yeah, same. So I would love if anyone comes up with it. Yeah, try using coordinates on me.
I coordinate first we will join O1 and O2 and assume
Okay,
that it is x-axis.
cool.
So O1 will be, let's say, a comma 0.
Let me just write it down. Wait. Yeah, so O1 is say a comma 0 and
And
O2.
O2 is b comma 0.
Right.
And then we could use distance formula
Yes. Okay, you are correct. So let's
x.
assume P is some x comma y.
Yes,
So
x,
what would your distance formula be?
x minus a whole square plus y minus 0. It is 0. It equals x minus b whole square plus y square.
Okay, here you are just taking OP1 square and this is
Okay,
sorry.
sorry.
Yeah. So what more do you need to do?
Radius also we have to consider.
Right. So here, okay, let me just move this a bit. So this is O1P squared minus R1 squared is equal to O2P squared minus R2 squared. So this is what basically this condition is, right? Written in terms of distance. So if you expand this, you'll see that the x square term cancel and the y square terms cancel. So basically this cancels. And what you'll be left out with is that you have minus 2xa plus a squared minus r1 squared is equal to minus 2bx plus x squared minus r2 squared. And here you have to assume that A is not equal to B if R1 and R2 are not equal. So we'll come to this why this is important. So from here we can get that. Okay, so from here, can you guys see that it will like X will basically be a constant? I'm not writing it down. So you bring this term and this term together, and all the rest are constants. You just divide. So can you see why X should be a constant from here? Is everyone with me?
It's because there's
Uh,
no Y.
Excuse me.
Yeah, sure.
Yeah. I think I have a different way to it. Like, for like all the we know that the like power of points if for both circles are equal, then there must be a common chord for that.
That is not necessarily true. So, for example, if you have two non-intersecting circles, there will still be many points which have equal power, right? But what you are saying, like, can you come?
Like if the circles intersect, then we can just draw the line of the common chord and
Okay,
join the center of the circles,
yeah,
and this is like the intersection is 90 degree.
yes. Okay,
Yeah,
so
so
from here, I
it
think
lies.
you're trying to say that all the points on this line are on the like satisfy this thing, right? The powers are equal.
Yes.
This is great, but there is one problem that you also need to show that any other point on the plane does not satisfy. So we want to qualitatively find out what exactly the locus is. So from here, we get that this line is a part of the locus, but we are not sure if this is only the locus. So this is a great approach, by the way. Like showing all the points on this line have equal power. You guys can try it out.
I think I might be able to try like a synthetic proof of this.
Oh yeah, go on.
So like let the centers be O1, O2, so we know that, and that let's say there's some point P which lies on the radical axis,
Okay,
and you drop a perpendicular onto this line O1, O2.
okay, let me change it. Here, I've intentionally drawn it right, but yeah.
Yeah, so let that be like to say M, and this would
Okay.
be M. So we know P O1 squared minus R1 squared, where R1 will be the radius of
Yeah.
the
Okay.
first
Sure.
will be PO2 squared minus R2 squared. So
Yes.
PO1 squared minus PO2 squared will be R1 squared minus R2 squared.
Yes.
So using Pythagoras, we can show that O1 m squared minus O2 m squared will be R1 squared minus R2 squared.
Yeah. So basically, PO1 square minus PO2 square will be equal to O1 m square minus O2 m square, right?
Yeah.
Okay. So what after this?
So we know R1 and R2 are fixed.
Yes.
So then so that means M, the position of M on this line should also be fixed, right? Because otherwise we will not have.
Oh, yeah. Yeah. True. Okay. This is nice. Okay. So from here, you get that since this satisfies, so all the points should also be on this thing. Okay, this one is cool.
Yeah.
Great, guys. Your name was Kaushal, right? Yeah. Nice. Right. So what he basically did is that, so you have this condition which you need to satisfy, and from P you drop a perpendicular onto O1, O2, which is say M. We don't know what M is or where M is right now. But from Pythagoras, you can show that P O1 square minus P O2 square is equal to O1 M square minus O2 M square. So this is basically because you have P you have M, this is O1, O2. So this square minus this square is equal to this square minus this square. That's basically what he did. And then he's claiming that R1 square minus R2 square is constant. So this value should also be constant. And since M lies on a line, like on the segment O1, O2, so this value should be like M should be fixed. And since M is fixed, so all the points which satisfy this thing will be on the perpendicular through M. This is nice. Yeah. Did everyone get this?
Like, can we also use kite, like kites, because like connecting O1 to A, like A and B,
Okay.
and then but no, it won't work. Yeah.
For that, I think you need a 90-degree here.
Yeah. Yeah.
I mean, it should work out because it is true, but you have to include weird cos angles and like trigonometry stuff, I guess.
Okay.
Okay, so like good digression, but let me just return to my if I'm completed. So from here, can you guys see that x should be constant? Like you can ask me, I can explain why. Okay, cool. I'll take it as a yes. So since x is constant and my y, it is independent of y. So basically what this locus will be a straight, a perpendicular line to the x-axis with a constant x value. And since my perpendicular line was O1, O2, or like here, so that means the locus is a perpendicular line to the line joining the centers. So that proves the claim. So are you guys okay with this? Is it fine? Also, don't try to use projective on the buffer problems. Like, try to do it simply. Projective would be like an oracle. Um, okay, I assume it is clear. Like, if you have any doubts, you can ask me. So now that we know that it is a line, so let's try finding a like radical axis of some common configurations. Can you tell me what the radical axis should be of these two circles?
Switch up on.
Just the
Uh,
line passing through
yes.
those 2 points.
So earlier we had found that these 2 points have like they should lie on the radical axis because they have power 0. So and we know that the line like 2 points determine a line and the radical axis is a line. So it should precisely be the line through the common chord. So this should be the radical axis in this case. And now for other like even if they're not touching, so the radical axis should lie somewhere over here. You guys can like manually calculate where this point M should be based on like whatever we did here. So that is quite helpful in finding where the radical axis intersects the line joining the centers. But now there are also cases where the radical axis does not exist. So remember when I said that we need A not equal to B. So what happens when A equals B? So in that case, I just get that this is my O1, which is A comma 0. And since A is equal to B, my O2 is also here. So this is also my O2. So the circles are basically concentric. And in that case, I won't get a valid radical axis because O1 P square minus R1 square equal to O2 P square minus R2 square. These terms will be equal. So I have to have R1 square is equal to R2 square, which is not possible. So in case of concentric circles, radical axis does not exist. So that's why I have to take A is not equal to B while solving this one. Okay, is everyone clear with this? Let's chat.
I have one question.
Oh, yeah, sure, go on.
If we assume that R1 is also equal to R2, just assuming,
Yeah,
so
okay.
the radical axis will be the whole plane.
Yes. I mean, we generally do not consider it, but it should be the whole plane.
Okay.
So, but since radical axis is basically considered when there are two different circles, So that is sort of a degenerate case. But yeah, it should be the whole circle, like plane. Okay, so now that we are done with radical axis, let's do a short. Okay, now let's do radical center. The next logical step. Okay, so we had two circles and we had a great time. Now let's introduce three circles. So let the circles be omega 1, omega 2, and omega 3. Okay, so uh, so what if we have something like this? Say this is omega 1, this is omega 2, omega 3. So from before, we have control over what the radical axis of two circles can be. So a natural thing to consider here is, okay, let me just denote the radical axis of omega 1 and omega 2 by this thing. So rad omega 1 comma omega 2. This represents a line. So if I use that notation, I know what rad omega 1 comma omega 2 is. I know what rad omega 1 comma omega 3 is. And I also know what rad omega 1 comma omega 2 is. And in this picture, it is very clear because this is omega 1. So this should be rad omega 1 omega 2. This should be rad omega 2 omega 3. What is it? Oh no, this was omega 2 omega 3. This is omega 1 omega 2. And this is the third one. So can you guys see any interesting concurrency? Sorry for my bad drawing, but yes, they concur. Can anyone try and give a proof of why they should concur? It's like, okay, you can speak.
Like
Okay,
take the
anyone
intersection of any two
okay,
of these lines, and then that point must have equal powers with respect to like the other two circles.
great. Okay, so that was a nice proof. So let's say the point of intersection P is of rad omega 1 omega 2 intersected with rad omega 2 omega 3. So what this basically tells us in words is that P has equal power with respect to omega 1 and omega 2. P has equal power with respect to omega 2 omega 3. So now notice that P has equal power with respect to omega 1 and omega 2 and omega 2 and omega 3. So that basically tells us P has equal power with respect to omega 1 and omega 3. Just based on these two interpretations. And now by definition, that implies that P belongs to radical axis of omega 1 and omega 3. And since it is discord, so okay, not discord, discord. So yeah, discord also should pass through P because P belongs to that power. Is that clear? Okay, yeah. I hope that was clear.
Can we try to use phantom points?
Random points. Okay, so
Like, mm,
yeah, I mean, phantom point is basically here. You can sort of frame this using phantom points. Like you can say that consider these two intersections and say this is P, like basically what we did. And then we show that P also lies on this line.
okay,
This
yeah,
is precisely what we did. So I guess this is a version of phantom
it's
points we
almost the
use.
same, yeah.
Yes. I mean, you shouldn't always think that what is phantom point or not. You just need to have the idea that I can sort of assume this arbitrary ghost point and then prove some properties assuming that point exists and then like get my required conclusion. So
Yeah.
phantom point is just fancy name. Okay, so now that we know this, we also need to know another case when radical centers do not exist. So basically here, whatever proof relied on was that these must intersect. But nobody has said that these will always intersect. So this might happen that this one is, let's say, omega 2, this is omega 1 and omega 3. and the centers are all collinear. So since the radical axis is perpendicular to the line joining the centers, these two lines, these are rad omega 1, omega 2, this is rad omega 2, omega 3, they will be perpendicular to the same line, so they will be parallel, and hence I won't get such an intersecting point. So in that case, we won't have a radical center because these themselves never intersect. So like even if we introduce omega 1, omega 3's radical axis, it will never intersect these two. So yeah, in this case, radical centers do not exist. Okay, is this clear? Come on, guys,
Yes.
I want to do problems. Yeah, nice. Okay, just a very quick application of this. Can you show that orthocenter exists? Existence. Look, I do not write E so bad. This is not my good. Existence of orthocenters. Sorry for the horrible handwriting. So let's say I have ABC and I draw perpendiculars like this, this, this. This is D, this is E, this is F. But why does orthocenter exist?
Oh, we can draw like
Like
cyclic
ADB and CF
circles
are
of
like
cyclic
radical
coordinate
axis.
rings.
A,
Okay.
B,
Yeah.
A, C are all.
Okay, so let's list down. Okay, you guys are correct. Nice. So let's list down the cyclic codes we can see up front. So we have this is 90, this is 90. So AFDC is cyclic. Also, this is 90, this is 90. So AEDB is cyclic. And this is 90, this is 90. So BFEC is cyclic. So now you have three circles and a natural instinct, also stemming from the fact that we just did radical centers, which had three circles, is that consider mutual radical axis, right? And see if this is useful. So if you consider this and this, you see that points AD are common between both of these circles. So these two have radical axis AD. Now if you consider these two points, what points? D, B, B. Okay, yeah, points B and F are common. This point, this point, this point, this point. So the radical axis of these two circles will be BE. And the radical axis of these two circles will be CF because point CF occurs in both of these. And now since we have radical axes, and of course, these centers are the midpoints, right? So center of AFDC is M2, which is the midpoint of AC. Center of ABDE is M3, which is the midpoint of AB. And center of BFEC is M1, which is the midpoint of BC. So these midpoints can never be collinear. So the radical center must exist, and hence AD, BE, and CF must conquer. And we fondly call it the orthocenter, denoted by H. So was this easy? I mean, it should be. If we consider there is okay, DDIT. What's your name? I don't know, sorry. But yeah, we'll come to that right after this. You have a good intuition of what's coming. Okay, so I assume this is clear. If not, just ask me. Explain it once more. But building on what DDIT is suggesting, what happens, we take point circles. Okay, so first let me explain this notion of point circles. Point circle is basically a very cool trick where you assume you have a point A and you assume there is a very small circle with radius 0. So it requires some justification that why we can work with this, but in Olympiad math, you just assume that like this point, we can define a circle with radius 0, and we can also consider powers of points with respect to this. So if you have point B and you have point circle at A, then power with respect to A, point circle of A, of B is just BA squared. Because, okay, if you want to understand this intuitively, it is like the power is drawing tangents, right? So the tangent square. Oh, okay, I just remembered. I forgot to tell one thing here. Very sorry. That, yep. So this value is also equal to the tangent square. Do you guys know this, or should I just tell a quick proof? PT square is also equal to this thing.
It's just connecting the center with.
Yeah, done. Yeah, good. Right. So now that we know that, so the power of b is basically the length of this tangent squared. And now imagine you're squishing this circle to a point gradually. So this tangent value is slowly becoming the value BA, which is what we consider here. So that is the notion of a point circle. Okay, is it clear? I mean, we will see more applications of why this is a very nice thing to have. Let's just do it right now. So say you have a triangle ABC, and now you consider point circles A, B, centered at A, B, and C with radius 0. So the circles are A, point circle at B, and point circle at C. So now again you have three circles. So you should think of radical axis here. And what's interesting here is that what is the radical axis of point circles AB? Can you guys like think and give me an answer?
The perpendicular bisector
Perpendicular bisector of AB.
AB.
Right. Right. Okay, can everyone see why this should be the perpendicular bisector of AB? Okay, I assume
Because
that's
they are
yes.
basically
Yeah.
circles, so properties of the radical axis of circle will apply.
So like
Right.
MA square must be MB square and it must be perpendicular because it's the line joining the center of two circles.
Yes, precisely. So we know that there exists a midpoint. So MA square is equal to MB square. And since the line joining the centers is AB itself, so this must be the radical axis. Let's call this M3. This should be M1. This should be M2. So again, if you consider the radical axis of BC, that will be the perpendicular through M1. And if you consider the radax through, okay, radical axis has a short form known as radax, which is very cool. So try to use that, guys. And if you consider the radax of EC, that is just perpendicular through M2. So a radical center says that they will intersect at a point, and we call this the circumcenter. And why is this the circumcenter? Because it is the center of the circle circumscribing ABC. And why is that true? Because OA is equal to OB because it lies on this perpendicular bisector. OB is equal to OC because it lies on this perpendicular bisector. And since OB is equal to OA is equal to OC, I can draw a circle centered at O, which passes through these points. So this shows the existence of circumcenter. I think I was a bit fast, but did you guys get it? We will do questions. Hold on. I think the next one is a question. Okay, yeah, sort of. Okay, so this was, let me just write it down. Existence of circumcenter. Okay. Now let's look at some nice applications of POP. So, oh yeah, short one. Again, let me write it somewhere. Radical axis is formally called as radax. Power of point is formally called as POP. Yeah, now application time. There is my diagram. Yeah, you have a triangle and there are two circles such that it passes through B and is tangent to BC. It passes through C and is tangent to AC. Sorry, BC again, right? Like this. So it passes through A, B, and is tangent to BC. Passes through AC, tangent to BC again. So another color, call this K. And if you join a K and you call this say M, so can you guys guess what M might be?
Midpoint BC.
Good. Now, why is that true?
POP.
Okay, can you just tell it for the sake of awareness?
MK into MA is MB square and is also MC square.
Good. So does everyone see why this is true?
Yes.
Okay, nice. And now let me draw a good diagram for this because this is going to be important. Never mind. Okay, this was a basic application of pop. Now let's just build on what we can do with this. So where is most? Yeah. We want to show that this K lies on the circle. Okay, I need another diagram. Okay, I hope this color is visible. So you remember DEF from the orthocentered picture, right? So this was D, this is E, this is F. And you draw this circle. Call this omega. So this omega is basically the circle through AFHE. And this is cyclic because we have 290 degrees opposite. So what we want to show is that K lies on omega. So claim K belongs to omega. So what my suggestion would be, or like a hint, is that you have midpoint. Try to somehow bring in the midpoint in this picture as well. So the midpoint should be somewhere here. And now join this. So basically you want this to be K. How is that possible?
Like, is it
Give
the
it a
Humpty
try.
point?
It is the Humpty point, but we
Oh,
are
okay.
sort of trying
Okay.
to build on that. It is Humpty
Got it.
point, right?
Okay, so you first try to prove that MF and ME are tangents,
Good,
and then you prove that MK into MA is MD square, which is you already proved.
right?
So A, F, K, and E must lie on the same circle.
Yes, you're right. Okay, so since he has already said that, so we'll achieve this in some steps. First, show that MF and ME are tangents to omega, and then use this to show that K belongs to omega. So can you guys try the first part apart from, yeah, I'm sorry, what was your name? Adyan, right? Or Sadat?
Sir, we can invert.
Okay, invert. Invert. Wedding
Invert
pop, right?
with radius MD.
Invert with radius MD. Okay, what will you got? I have never done that.
Sorry, MB.
MB. I mean, yeah, you can always invert, but since you're doing pop, I really don't want to go into inversion.
Like, we can just angle chase, I guess.
Yeah, this is basically just angle chase. Save inversion for later. We'll need it. Yes. So yeah, you know MF and MB are equal because M is the center of this circle, BFEC, right? So this was B, so this is B. So this small thing is 90 minus B. How is it useful? Yeah, that is 90 minus B. This thing is 90 minus C. Can you guys see why this is true? Because we have a 90 here, we have a C here. Let me write it down. Okay, this is B. So this small angle is 90 minus B. This is 90 minus C. So this small angle is 90 minus C. So this angle adds up to a total of A. Similarly, this angle is equal to A. And since this angle is A, we get that MF and ME are tangents. Cute angles. Okay, did everyone understand? I'm not sure. Okay. Cool. Just ask me, I can explain it again. So, uh, I'm assuming we are done with this part. So ME and MF are tangents. Now, what this basically tells us is that, okay, we can use again phantom points here. So what are we assuming? We are assuming that let's take AM and say it intersects omega again at K dash. We don't know what K dash is. We want to show it is equal to K, but let's just assume that this intersection is K dash. So what do we get? We get that power of M with respect to omega is mk dash times ma. That is also equal to the square of the tangent. So this is equal to mf squared. This is also equal to m squared. Right? Okay, is everyone with me? Oh, sorry. Yeah, I should start. Wait, you guys just wait. Okay. I mean, if you want, I can re-explain any part. It's fine. You can also like personally DM me. Okay, cool. So, is everyone clear with this? Just give me a yes. Till whatever we have done.
Yes, yes.
Okay. So I'll continue. We have this. And now we know that MF is equal to MB. So this is also equal to MB squared. And what we know from here is that MB squared is equal to MK times MA. So this is equal to MK times MA. And now we can finally equate these two, get rid of MA, and we can say that MK is equal to MK dash. So this should imply that K dash is basically K because both lie under ray M. So this implies that this is true. Was this proof clear? Okay, nice. Um, okay, I have a lot of things to cover. Do you want to do a small problem or a bit of theory first? Okay, let's discuss a problem. Which one shall we do? Oh yeah, the second one. So just to sum up in the last part, what we did is that we have also conclusively shown that if this is the orthocenter, then HK will be perpendicular to the A median. That's it. You can try relating these two and see why this should be true. Now let's do a problem. Okay, you guys shouldn't be scared, but this is Chinese national. No. I mean, do not get afraid. I just wrote it randomly. Trust. I mean, the problem is not that hard. Just like, yeah, exactly. 2007 in scale, and it's not hard. Let's do this quickly. 5 minutes, shall we? I'll draw a diagram. So we have A, B, C. Circle with diameter AB intersects CA and CB, and at M and N, it's just a long way, like bad way to tell that we just drop perpendiculars. This is M, this is N. Okay, never mind, I need this. And so they are claiming this is T. Now we have a one nice construction is that we extend AN and we see this. This is S. We need to show that BS is perpendicular to S. So this is 90. This is what the problem is. Okay, try thinking about it for like 3 minutes and tell me if you have any thoughts. Let me read the chat again. Okay, so I have got a question that is in radical centered part. Uh, if there are three circles such that exactly two of them intersect and the centers are not collinear, then will the center still exist? The answer to this is yes, it will exist because even if you have, let me just draw it on the side. So if you have this and this, and then you have another circle, so the radical axis of this is this, of this may be something like this, and of this may be something like this. So the radical center will exist, but it will be outside the like all the three circles. So it's not necessary that all of these must mutually intersect. Is that clear, Harshit? Okay.
Okay, sir. Now my
No,
thought
wait, don't call me sir.
is
Don't call me sir.
okay. Uh,
Just call me
we
Debarchan.
have that we have that BTS square is equal to BN into BC because BTN is equal to BAN is equal to TCB. Then we get
Can you just
that
repeat that angle chase? I'll do it.
okay. BTN
BTN, okay.
is equal to BAN
Right.
is equal to TCB.
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 Yes.
Then we also have that BS square is equal to BN into T into BC.
BS square
Then
equal
we
to
uh, BS square is
BC
equal
square.
to BN into BC.
BM into
BN
BC. Okay, BM
BN
into.
into BC.
Okay, we need to show that, right?
No, we show it because BT is equal to BS.
Right. Okay, so you're basically done.
Yes.
Nice, nice. I'll give everyone else a moment to figure that out. But nice. Let me write it down. I guess there is
How are we done after this? Like BS squared equals
I
BN.
haven't told yet, but try thinking about it. I'll tell the solution in a minute. So
Does taking a
what the
degenerate,
yes
does taking a zero circle at B help?
at B, you need to show BS is perpendicular to SC, and for that, when it might help is that if you have 2 points and you need to show perpendicular thing. So here, if there would have been another point here, let's say D, such that D is also a point circle, then you could have done some
Oh,
radical
yeah,
axis
yeah.
stuff and so.
Yes, yes. Okay,
But here
okay.
you have only one
Understood.
point. So I don't think that
Yes.
is quite helpful. But that's a nice intuition to have. Yes.
Okay.
What your motivation should be is here, try to backtrack. Yeah. Backtracking is like the easiest. So what you do is you assume that the final thing is true and deduce what should be true based on that. And optimally, that deduction, that thing you need to deduce should grow easier and easier. Can you guys see my Discord or only that my screen? Oh, okay. Let me tell it now, I guess. Does anyone else have any other ideas before I like spill over the solution? I assume that's a no. So let me just start. I don't know how to solve this problem. How can I solve this? So I want to show BS is perpendicular to SC. So that should be a 90. And I already know this is a 90. So I have a triangle like this. So what this means is that if this should be true, then I should have BS squared is equal to BN times BC. This is a must. And if I have this, I'll also be done. So I want to show this relation is true. So I now want to figure out what Bn times Bc can be. Also, Bs, that has been conveniently said that it's equal to Bt squared. So what my problem reduces is to show that Bt squared is equal to Bn times Bc. And if we can show this, we would be done. So this is what I meant by backtracking. Assume this thing is true, and then sort of make slightly easier claims that you can try and prove. Okay, let's call this MNK. Nice. So what is Bn times Bc? Can you just give me a nice name for it? I mean, any other relation you can get? Anyone? Wait, I'll explain Sadat's proof in a bit, but like here, can you tell me what we should do next? AB square, not quite. AB square times what? Yeah, BK times, not KA, BK times BA. Nice. That was a typo, I'm pretty sure. So you have this is true. So now you're reduced to showing that this should be true. So focus on this triangle, guys. You know this is a 90 because T lies on this circle with diameter AB. And you also know this is 90. So isn't this like, not obvious, but isn't this true now? Can't you claim it? Yeah, DDIT, you're right. It's quite. Um, guys, come on, we have to finish this fast. So, can you see why BT square is equal to BK times BA based on
Yes.
whatever is in this? Yes, nice. Okay,
Similar
here.
triangles.
Right, similar triangles. So, this is true if and only if bt by bk is equal to va by bt. So, and you know that bt by bk is, so triangle tbk is similar to triangle a b t, I guess. I mean, yeah, you can figure this out. This is true because this is 90, so let's call this theta. So this is 90 minus theta. This is a theta. Sorry, this is a 90, so this should be theta. So we get two triangles, this and this are similar. So from here we get this relation. And since bk times ba is equal to bn times bc, we get this relation. And since bt square is equal to bs squared, we get this relation. And this is what we wanted. So we are done. I think I was a bit fast over here, but did people get it?
Yes.
Okay, others?
Yes, get
Okay, nice. So yeah, that was a Chinese, no problem. But 2007, dinosaur age. Let's do problems. Yeah, I don't want to do in theory. I can do it later in another class, I guess. Okay, I can give you guys homework for that. Never mind. Let's do this please. This is some, okay, I'll again scare you, but don't get scared. This is pretty not hard.
I did this using projective geometry.
Okay. Um, the others take a screenshot or maybe write this problem. Meanwhile, I'll listen to your solution. Just a moment. Others take a screenshot, please. One, two. Okay, fine. Yeah, tell your solution. I'll draw it in. In M, say somewhere we have T. And the T should be here. This is this. Yeah. Tell your solution. Directed angles you could have used, but yeah, I'm not pretty good with directed angles myself. Okay, who had a projected solution?
No, I meant the other problem, P1.
Okay, sorry.
Mm,
Yeah,
I
that
I
has
I
been.
know something about GD intersect the circumcircle. That is the point
Parallel
where
to BC.
uh,
Yes,
2011 I am a problem.
right, that radical axis, like some intersection, I forgot. Yes, you need that. So let me just, who the hell calls a circle C? Here you have G, somewhere. I guess this is D. So you have AG meets C at M. This is, where is, okay. N, prove that, and F. These are our normal nice points. Yes, Adit, what was your thing?
So like we
Sadat?
need to show that FE, BC and MN will conquer at some point.
Yes. So here if you backtrack, so assume this cyclicity holds, never mind when doing. So you need to show that FE, BC, and MN conquer. And now you would be done. So how will you show this thing?
Like we can cross ratio chase and finish, I think.
Fine. But no, this is a top class. So you should do what's popular.
Yeah, I'm trying that,
And
the pop one.
Saddat had a very nice point. So where is he? Pascal. Pascal and what? Like, tell me.
It has that
Ah,
DG A prime are collinear. I mean,
okay. So
where A prime is the reflection over the perpendicular bicycle.
yes, this is a property in itself. So let A dash be such that A dash CB is isosceles trapezoid. This is just another way of saying that it is reflection. Then you have G, DG A dash collinear. Do you know the proof of this?
I think it was using phantom points.
Yeah, you can like do using phantom points, but there is a more direct proof. I mean, okay, phantom point works. So how do you want to do that? Sadat, do you know the proof of it? Yeah, I think this problem might take a bit longer than I expected. There
Okay,
is,
if
yeah,
this claim is true, then we can take AM intersect BC.
yes,
AM intersect BC.
that's true. But I'm asking that, do you know the proof of this? Like, it's fine if you don't.
I know, but for what?
It's fine. I also forget a lot. So, yeah. Okay, does anybody else want to try why this should be true? Let's assume this is true. Okay, assume this thing holds. So, this
Then
is parallel to this.
then then we have that AM cap BC D and M are cyclic.
Okay, so let's call this D, E, F, G, H, I, K, J.
Then we also have that E F D G are also cyclic
That is
because
true.
G is the midpoint.
It is not the midpoint, but 9 point
Midpoint
circle.
because G 9 yes 9 point cyclic. Then we also have that DG and M also cyclic.
Yeah, okay, let's not get ahead of ourselves. So I'll tell why this is true. This is a very nice property and you should keep this in mind. So if you have a triangle ABC and a circle like this, and A dash is your, or like, you draw parallel to BC, you get A dash. And now you want to show G, this thing. These are collinear. So do all of you guys know about 9 point circle? So it is basically a circle passing through the midpoints and also the feet of perpendiculars. So these are 6 points as of now, but more three will come. Like the midpoints of the line joining the vertex and also center, which we don't need now. So what basically we want to do is that these conquer at G, right? Now you take a homothety with radius with ratio -2. So what this does is it takes this midpoint of BC to A, it takes the midpoint of AB to C, it takes the midpoint of AC to B. So this 9 point circle maps to the circumcircle of ABC. So wherever D goes, D, let's say it goes to A double dash, then we have that, and let's say this is M. So we have DM is parallel to A dash, and A dash belongs to ABC from the homothety itself. So since this like this is this point. So we know that A dash is equal to A double dash. And since D, G, A double dash are collinear, D, G, A dash is also collinear. I think people might have issue with this, but is this fine? Harshit, you don't need 9.2. Okay. So it is basically a circle passing through the midpoints and the feet of perpendicular. So midpoint, let's say M1, M2, M3, and the feet of perpendicular DEF. So this will be, these all points will lie on a circle. So this is basically a 9-point circle. But what is Y? Isn't it illegal to use 9-point things in pop glass? I mean, no. Okay, fine. Words. It's not illegal, but yeah, I'm a dictator now, so you can't do anything. Okay, try seeing why this is true. In Y, BCEF, BCMN. Okay, wow. Yeah, fine. So assume this is true. Okay. So what also we get from this is, since the ratio GJ divided by AG is 1 by 2, because G divides the median in the ratio 2:1, and this is also equal to G D divided by G A dash, we get that G D is equal to thrice of G D is equal to G A dash. So is everyone clear on how we got this relation? Like, let me highlight it, looks nice.
But it's similarity because they're parallel and
Yes.
yeah.
In projective proof, I mean, I haven't heard the projective proof, so I can't comment. But you can show the like concurrency easily using project proof. Okay. Now we know this thing, right? Okay, let's work a bit faster. So now, can you tell me what? Okay, never mind. I get it. It's nothing great. Can you see why this is true? This is the very first thing we did in class. Give me a yes, I guess.
Yes.
Thank you. Also, we have this. So, what do you want to do? You can replace GA with GJ. Sounds funny. And you can replace GA dash with GD. So, doing that, you get 2 times GM times GJ is equal to 2 times GN times GD. And now, if you cancel this, you get GM times GJ is equal to GN times GD. So, GM times GJ is equal to GN times GD. So, what does this mean from the converse of that? Okay, hello guys, wake up. Okay, fine. Yes, I'm getting yes in the chat. So, uh, okay, that shouldn't be yes. Fine. So this basically tells me that DJMN is cyclic. So can you see why this is true?
9-point circle.
Yes, sorry.
9-point circle.
Not 9-point circle. I'm
Oh,
telling
sorry,
you
sorry.
these
I
four.
thought, oh, DGEF I was talking about.
Oh yeah, they are also like cyclic. Yes, that's 9-point circle too. But
Yeah,
why is
so
this?
DNM is actually equal to DGA, which is equal to JA dash.
Oh, are you trying to angle change?
Yeah. Angle is
I mean,
also a sir.
uh, it might work. Okay, it works. Okay.
It's just like
But
the PowerPoint.
yeah, but here we have a easier thing. So we already know that GM times GJ is this times this is equal to this times this. So using a converse of pop, we can directly conclude. All right. So we now have some nice circles. We know FEDJ is cyclic because of the 9-point cycle. We know DJNM is cyclic. We need one other cyclic. So what could it be? I mean, okay, you might. Let me just check what I did earlier. Hmm,
We can take the circumcircle of ABC.
Circumcircle of ABC, yes, can take that.
We can
So
also take
from here,
BFEC.
nice. Let's just list down what all possible things we can take, and then we can just sort out which is required. Okay, we have enough circles now. What is the radical axis of the green circle and the yellow circle? It is not something nice. Never mind. We won't use that. What is the radical axis of pink circle and yellow circle? That is DJ, which is nice. And then what is the radical axis of pink circle and the green circle? That is MN. And the pink circle and the orange circle is EF. But these are not the same circles, so we can't conclude they concur. We need one more circle. Wait, I think we can frame it in a better way. Let me just Okay. Let's give this circles a name. This is circle C1. This is C2. This is C3 and this is C4. So considering C1, C2, and what? Okay, no, this is good. Okay, help me out. C3 and C2 have DJ, C1 and C4. Yes, that's true. How did I do it previously? Okay, so my notes say that I need FE times, okay, let's say FE intersection BC is L. So what do I get? I get LF times LE is equal to LD times LJ. And LD times LJ, so LF times LE is also equal to LB times LC. Oh, okay. Can you see why this is true? Um, I okay, nice.
Yeah.
And now let's say this is also sort of phantom point. So I tried to do this using Radax, but directly I failed. So it's just totally. What did I call it? P. So now if you have say this was L and say this is P for the sake of contradiction, I guess. So here you have Pn times Pm is equal to Pd times Pj because DJMN is cyclic. And Pm times Pn is also equal to Pb times Pc. Okay, is this all right? Mm, Okay, this is alright, guys. Like these two things. Okay. No, I won't do mn times of I would just conclude using something easier. LB times LC and LD times LJ. This is the power of L with respect to ABC, circumcircle of ABC, right? And this is the power of L with respect to the 9-point circle. Call the 9-point circle omega 9. This is not standard, I just made it up. Can you see why this is true? Because the 9-point circle is this. Okay. And also here, this is power of P with respect to circumcircle ABC. And this is power of P with respect to the 9-point circle. So what I have here is that I have a line BC and I have, okay, consider the radius of ABC circle and the 9-point circle of ABC. That should also be a line, right? Now, case one, it is a line which is not like coinciding with BC. So it must intersect at exactly one point. So in that case, I get P is equal to L and I'm done. And case two, it is equal to, like, it coincides with BC, but well, it can't happen because at some point I have, like, at some point I have one point in BC is inside the circumcircle, and at other point I have this also outside the 9-point circle. So it cannot be BC. So it must be another line which intersects BC at most one point. So from here I can conclude P is like same as L. And from there, these two equations will then give me FEMN cyclic. Yes, that was a bit scuffed. But this is not epic. I think I screwed up, but this is a good, like, valid solution. Did people get it? I mean, I can re-explain. I think I messed up over here. So is like every part of the proof clear? Just okay. Thank you. All right. Okay. So I think I have one more other problem. Random source. Or I have some nice theory part. Okay, let's just do this. This is important. I wanted to discuss this. So another cool application of pop, basically. In triangle ABC. This will be the last thing we'll do, and then I'll leave some for the like homework if you want to do. So O is the circumcenter, and I is the incenter. I hope everyone knows what incenter is. So it's basically the intersection of angle bisectors. And let's say R is the circumradius, and small r is the inradius. So radius of the incircle and radius of circumcircle. So show that OI square is equal to R square minus 2RR. This is known as Euler's relation. Okay, projective solution after I discuss this. What, how? Really cool. No, I didn't. Oh yeah, this relation does hold. Try to show. I mean, try to backtrack and get how this can be done. We have used almost every idea that is required to solve this. Okay, so do people have any ideas? Also, I'm really sorry for the overextension of the class. Like, if people want to leave, it's fine. I think the recording will be available, but I'll just finish this and leave you guys. Sorry for that.
Like we can take AI intersection the circumcircle and then call it D,
Cool, cool.
and
So
then
let
we
me
take that.
motivate it for the rest. Yes, you were right. So let me just motivate
Yes.
it for the rest of the people. So rearranging this, I want to show minus 2RR is equal to OI squared minus R squared. So basically what I want to show is the power of I with respect to this ABC. The mod is equal to 2RR. And we have already seen that whenever a power is included, we always want a nice chord that we can control. So what is a nice chord that passes through I and we can have some nice control over it? I think Zohad had something. Zohad, do you want to tell your chord?
Like AI cap circumcircle.
Right. I mean, it would also have been BI and CI, but I love AI.
Yes.
So let's call AI cap ABC as L. So what is this value? The mod of this is just AI times AL. So I would be done if I show this thing is equal. Uh, now, intuitively, you should know that you have already solved the problem because AI is very well known. I mean, you can formulate it using the coordinates of the measurements of the triangle. And AL is also very well known. So, okay, what do you want to do? Okay, no, sorry, not AL. What am I doing? IL. Do you want to lead us forward, Zohad?
Like we can take the L antipode and then work with that. I think
Yes,
so.
you are right. Yeah, that can be done. But there is a really
Yes.
easy way to do this. Do you all know incented incent lemma?
So
Incented
yeah,
and
LB
center.
equals LI equals LC, and that
Yeah,
also I
so
think
I can
helps.
replace Li with Lb, right? This is still equal. And now what is AI? AI is nothing but, if you look, this is A by 2, and this is the in radius R. So AI is nothing but R by sine A by 2. And what is LB? LB is nothing but 2R times sine A by 2. This is from sine rule. And this is from that like triangle AI. Let's call it TEF, the in touch points. So AIF. And now if you multiply them, you get this cancels. So you'll be left with 2RR. And this finishes the problem. So yeah, Shreyas, you can see that this is indeed true. So this is another way you can use like PowerPoint stuff to motivate solutions. The main idea here was take a nice chord. That's it. And it should be this chord. Uh, okay, so I think I'll stop here now. So do you guys have any questions?
Don't do it the positive one.
Oh, okay. Projective, can someone tell me what they had in mind? I know that this will be done using projective, but I did not do it myself.
I guess involution because we have PP, BB, PP, BC, DG are involution pairs.
Okay, fine. Involution is a bit too hardcore for this Bechara problem, but yeah, I trust you. I think it will be done.
Because we can project from A, then we get P goes to QA point, and then from where we can done.
Okay. I also wanted to discuss the radical axis stuff in the orthic triangle picture, but I didn't get time. So what I will do is, I think it can also be done using projective. The next problem which I had in mind uses projective. It's like a one-liner, but I'll send that and also like the walkthrough of the orthic triangle picture and the radical axis in the notes, and probably you can like complete it to yourself. If you have any doubts, you can contact me on Discord. I hope you know my like ID. Like any other thing you want to say before I end this class? Let me stop the recording. Yeah, I'll send the notes along with what I wanted to share. How the hell do I stop recording?